Hello everyone, my name is Li Liu from Huazhong University of Science and Technology. Today so happy to be here to introduce our work, a data-aware learned index scheme for efficient write. Traditional index structures such as B-tree family have large index size when facing large-scale datasets, resulting in high memory occupation and low search efficiency, which seriously affects read and write performance. The learned index opens up a new paradigm for indexing that uses models to replace the traditional index structure and to predict the position of a record. Since the number of model parameters is much smaller than the number of pointers in inner nodes, the space taken by the index is significantly reduced. The key idea of learned index is that any index structure can be regarded as a model for mapping a lookup key to the record position in a sorted set, such as B plus tree. For a given key, B plus tree goes through two search phases to pinpoint its record position. First, B plus tree searches the key layer by layer from the root node until it reaches the corresponding leaf node, and then perform a binary search in the page to obtain the actual position of the record, and the page size can be considered as a margin of error. Similarly, a model can learn the sorted order of search keys and use this information to effectively predict the position, such as a single-level neural network model. Due to the inevitable deviation of the learned model, it is necessary to record the maximum and minimum errors of the model during training, and further determine the accurate position in the error range. To reduce the prediction error and speed up the lookup performance, the learned index schemes usually construct multi-layer models recursively, that's the recursive model index, the famous IMI, so as to divide the large-scale dataset into many small subsets, which not only improves the learning efficiency, but also is easy to learn with a simple model. However, IMI is inapplicable to dynamic workloads because it performs uniform data distribution based on cumulative distribution function, and it is likely to put the two records far apart into same data partition, resulting in large errors. And IMI has poor scalability and unacceptable write performance. When new data is inserted into IMI, it has to migrate all the data after insert position in the sorted array, which severely affects the write performance. In addition, with the continuous insertion of new data, model errors will expand. To ensure the prediction accuracy, all IMI models has to be retrained after several writes, resulting in unacceptable write performance. Some research has been conducted to solve the two problems of IMI, such as fitting tree, Alex, PGM, X-index, F-index, etc. However, they still have limitations. Fitting tree keeps the structure of inner nodes as in B plus tree. It requires more memory space. Alex and PGM index reserve empty slots for new data in the trained data array, which requires more memory space and shifts overhead. X-index divides data into different groups with partition algorithm, and each group includes a data buffer to handle inserts, which leads to the write blocking and poor range query performance. F-index appends a dynamic linked list structure under each trained data to process new data, affects read performance. Thus, how to achieve a better balance between write efficiency and memory cost still needs further exploration. In this work, we propose a data-aware learned index scheme that supports efficient write. We call it LYLI, which is capable of adaptive adjustment according to changes in data distribution, while supporting efficient read and write operations with a lower memory footprint. We explore a lightweight data partition algorithm for various workloads, which ensures that data partition always tends to be linear. We propose a data-aware learned index structure that realizes self-adjustment. When the data distribution in a leaf node changes, it can automatically extend in horizontal or vertical directions, efficiently support writing and slightly maintenance for learned indexes. We designed dual buffers, including a mutable buffer and an immutable buffer, to handle new data in an asynchronous way, which supports efficient writes. We implement evaluate and evaluate on various synthetic and real-world datasets. Here we introduce the overall design of evaluate. A figure depicts the architecture of evaluate, which consists of three parts. First is dynamic data partition, and then is a data-aware recursive model index, called dummy, and the incremental buffer. Later, we will introduce the three parts in detail. First is a data partition algorithm. An efficient data partition algorithm should be able to adapt to different workloads with low model error and time cost. We analyzed several partition algorithms, including shrinking cone, CDF, ASAM, and k-means. The partition efficiency of shrinking cone is affected by the predefined error threshold, while the CDF, ASM, and k-means algorithms are mainly affected by the predefined number of data segments. For fair comparison, we establish a mapping relationship between the number of segments and the error. First, we preset the error threshold for the shrinking cone algorithm and use it to perform data partition to obtain the number of data segments. Then we use this value as a default number of segments for other algorithms, as shown in this table. Then, as shown in figure split time, we find that the partition time of shrinking cone, CDF, and ASM is relatively stable and not affected by the error threshold or the number of segments, while the k-means algorithm is significantly affected by the number of segments. As shown in the figure of split error, the model error of shrinking cone and k-means is far smaller than ASM and CDF. Therefore, we choose the shrinking cone algorithm for data partition. And the shrinking cone algorithm partitions the key space into variable-sized segments according to the data partition. Use piecewise linear function with an error band error, which achieves a good balance between lookup cost and space consumption. Then we introduce the data-aware recursive model index, called the dummy. After data partition, the leaf node is independent of each other, enabling flexible index structure adjustment. When the data distribution in a leaf node changes, leaf node is automatically split in a horizontal or vertical direction, and the corresponding model is retrained dynamically, enabling high prediction accuracy. Later, we will introduce the initialization of dummy, model retraining, node split, and when to retrain dummy. When initialize dummy, it adopts a bottom-up approach to build a model of each layer and select a two-layer architecture to speed up the keys mapping. First, the data is divided into multiple segments by shrinking cone algorithm. The lower limit value of the first data segment is set to -infinity, and the upper limit value of the last data segment is set to infinity. Then, each leaf node is trained based on its data segment using a piecewise linear function. The independent variable is the key of the record, and the dependent variable is the position of the record in the sorted data segment. Then, we construct a linear regression model for dummy's root node to find its submodel. The independent variable is the lower limit value of its data segment. If the lower limit value is -infinity, replace it with 0, and the independent variable is its position in the list of nodes at the same level. In dummy, when the new data is merged into the data segment, it leads to position shift of the data, and the original linear model will fail. As shown in the figure, we want to find the 32. After few data inserted, the position shifts. We cannot find the 32 within the error band. At this time, the daemon will check whether the data distribution in the data segment changes. If it changes, it will rescan the related data segment and retrain the model. Since model training is performed in the background, system can handle read and write requests without blocking. Why it needs to split a leaf node in dummy? When the number of records measured by a leaf node exceeds a certain threshold, it is necessary to split a leaf node into multiple nodes. On the one hand, too many records in a data segment will increase the amount of data to be scanned for training, which will sharply increase the training cost and seriously reduce the write performance. On the other hand, if a linear model is fitted with too much data, its accuracy will also degrade, leading to poor performance. Dummy provides two ways to split leaf nodes according to the data density in a data segment. That is horizontal split and vertical split. As shown in Figure A, for horizontal split, the original leaf node is split into multiple sibling nodes, and their parent node is further trained. As shown in Figure B, for vertical split, the original leaf node is split into multiple tail nodes. Dummy will train a new parent node model to merge multiple newly created leaf nodes. Each time a vertical split is performed, Dummy's depth increases by 1. Dummy will dynamically select the split weight based on the data distribution. If the data segment contains minus infinity or infinity, it means that the range of key can be inserted is larger, and this node is more likely to be split in the near future. In this case, the node is preferred to split horizontally to avoid index structure be skewed. For other data segments, it decides the split weight according to the density of the data segment. We call it sigma, which is calculated in the equation, where n is the number of records in a data segment, and the max key is the largest key, and the min key is the smallest key in the data segment. In our work, the threshold of density is set to 0.9 according to experimental parameter tuning. If a sigma exceeds the threshold, it means that the key distribution in the data segment is dense. Fewer keys are allowed to be inserted, and it is less likely to be split again. In this case, vertical split is recommended. Otherwise, horizontal split is recommended. When the height of dummy reaches the threshold, in this study we set it at 5. Dummy is trained to become a flatted structure, because the height of dummy significantly affects read performance. Dummy's training is very efficient. It only needs to retrain the model of root nodes. All leaf nodes can be reused and not to be retrained. For the incremental buffer, Awali adopts dual buffers with the same size to handle incremental data. One is for receiving new data and keep the data in certain order, called mutable buffer. The other is used to merge data into dummy in the background, called immutable buffer. When the volume of incremental data reaches a threshold, the mutable buffer is turned into an immutable buffer, and the background thread is awakened to perform the data merge operation in batches. At the same time, a new buffer is created to handling subsequent writes, and after the merge operation is finished, the immutable buffer will be freed. Next, we evaluate Awali and compare it with B plus tree, IM model, fitting tree, and X-index. We compare them with two real-world datasets, that is NYCT from taxi passenger records in New York City, and OSM, the dataset of OpenStreet Maps, and one synthetic dataset, the non-normal. And we use several different workloads with reference to YCSB benchmark. We first show the experimental results of read and write performance as shown in Figure A. On the read-only workload, Awali performs better than B plus tree and fitting tree, but performs worse than X-index and IMM model. The reason is that the non-leaf node of Awali uses a linear regression model to select the next layer, leading to a further binary search within the error range. When x-index in the IMI model uses a CD function to calculate the position of the next layer model, which is much faster. Also, the dual buffers of L-Valley affect the read performance because it has to perform another twice binary search. As shown in Figure B, on the write-only workload, L-Valley performs best, and the reason is that L-Valley adopts the dual buffers and the delay update mechanisms. The sorting and merging are done by the background thread, which greatly reduces the write blocking. Then we show how L-Valley performs on the mixed workloads. As shown in Figure A, on the write-read balanced workload, there are 50% read and 50% write. L-Valley improves the overall throughput over B plus tree, fitting tree, and X-index. As shown in Figure B, on the read-heavy workload, L-Valley performs better than P plus tree and fitting tree, also a little worse than X-index. Now we show experimental results of short-range scan and memory usage. As shown in Figure A, the overall throughput of L-Valley is lower than B plus tree and fitting tree, but performs better than X-index. The reason is that when performing range query, L-Valley needs to obtain the targeted result from dual buffers and sorted array, which increases cost. As shown in Figure B, for the memory usage, L-Valley requires more memory than X-index because L-Valley needs much more space to store model parameters. And more experimental results are shown in our paper. Here is the conclusion of our work. In order to enable the learned index to provide efficient writes, we propose a data-aware learned index scheme called L-Valley, which achieves better write performance. L-Valley partitions data based on shrinking cone algorithm, which can ensure that any data distribution can be learned with simple piecewise linear function. L-Valley implements a data-aware recursive model index dummy. Dummy can adaptively perform node splitting and retraining according to the change in data distribution, and dynamically adjust index structure. In order to support efficient writes, L-Valley designs dual buffers to handle incremental data in an asynchronous way, and merge the new data into data segments in the background. L-Valley improves write performance by more than 6% and 33% than fitting tree and X-index, while maintaining efficient read performance. That's all. Thanks for your attention.